So this video is about representing numbers in different bases. This is extremely useful because in computer science or in computers, everything is stored in binary representation instead of decimal representation. So internally, your software is constantly changing everything you're inputting into binary. And so we're going to see how it's done. So with that, let's start with recalling what decimal expansion means. So when you write a number in decimal, let's say 25, what it actually means is you're doing 2 times 10 to the 1 plus 5 times 10 to the 0. So let me put one more digit. So let's say I'm doing 625. Then that is 6 times 10 square plus 2 times 10 to the 1 plus 5 times 10 to the 0. Okay, so let's give names to these things. This is called the decimal expansion, if you will. Then 6, 2, and 5 are the digits. And the 10 is the base. So more systematically, what we should write is 6 to 5 in base 10 is 6 times 10 square plus 2 times. Now, of course, in everyday life, we only deal with base 10. So we skip that bracket n to the base 10. But it's always there, even if we don't actively use it. Okay, so that's what we mean when we write digits, that the rightmost digit is multiplied by 10 to the 0, then the next digit is multiplied by 10 to the 1, and the next digit is multiplied by 10 to the 2, and so on. Successive digits get multiplied by higher powers of the base. Okay, and so now let me put those. So properties of decimal expansion are that you have digits which are either 0, 1, 2, 3, or all the way up to 9. Why 9? 9 is, notice that 9 is 10 minus 1. So we go all the way up to base minus 1. And then the digits, or actually that's it. So that's all we need about, this is what the decimal expansion represents. So now we want to change from decimal to binary. What the first change we'll make is we'll make the base to be 2. Okay, so it's the same concept, but we are changing 10 to 2. Now the digits have to go from 0 all the way up to base minus 1, and base minus 1 is 2 minus 1, which is 1. So the digits are only 0 and 1. And I can form any number using just digits 0 and 1. So for example, I can form 10101 in base 2. And this is a valid number. What this means is I'll start with the rightmost. I'm doing 1 times 2 to the 0 plus 0 times 2 to the 1 plus 1 times 2 to the 2 plus 0 times 2 to the 3 plus 1 times 2 to the 4. Just so that we're clear on where things are coming from. This one is this one. Then we have this 0 is that 0. Then we have this one is that 1. Then this 0 is that 0. And if you want to find out what this number is exactly, you will do 16 plus 0 plus 4 plus 0 plus 1, and that is 21. But this is in base 10. Okay, so 10101 in base 2 is the same as 21 in base 10. So that's how digits in different bases represent numbers. You can have higher bases. So for example, you can have the ternary base. Here the base is 3. And because the base is 3, the digits are 0, 1, 2. And let me just do a quick example. If I wanted to do, so I can form any number using 1, 0, 1, or 2. So I can, let's say, do this. base 3. So then I'll start from the right. I'll get 2 times 3 to the 0 plus 0 times 3 to the 1 plus 1 times 3 square. That is 9 plus 0 plus 2, which is 11. Okay, so that's how you represent, sorry, here 11 is in base 10. Okay, so that would be a ternary representation. Then the more interesting one that you will encounter a lot, especially in computer science or programming, is the hexadecimal. So the hexadecimal representation uses 16 as your base. And in this case, the digits are to be from 0 all the way to 15. Now, the problem is that if you use these digits, then when you write a number, you will have to bracket things so that you don't confuse with 11 and 1 1. So just to give you an example, actually, so this is not the digits that are used for hexadecimal specifically, because hexadecimal is very common in programming and it's annoying to have to bracket things every time. So what we do instead is we keep the first 10 digits and then we start using letters. So we'll do A, B, C, D, E, and F. So A stands for 10, B stands for 11, C stands for 12, D stands for 13, 14, and 15. So they are just substitute placeholders for the double digit numbers. Okay, and now I can express something in hexadecimal using these digits. So for example, I can do 1 F F 0, let's say. Then this will be 0 times 16 to the 0. This is in base 16 plus F times 16 to the 1. There's no such thing as a F. F is 15 plus, let me change the digit A. A is 10, so 10 times 16 to 2 plus 1 times 16 cubed. And I don't really, okay, 16. The reason 16 is used in computer science is because 16 is 2 to the 4, and binary powers of 2 are easier to encapsulate using microprocessors because the bytes come in powers of 2. So this is 2 to the 12, 2 to the 4 to the 2, that is 2 to the 8. 2 to the 12 is 4096. 2 to the 8 is 2 to the 4 whole square. 2 to the 4 is 16. So that's 256. So that's 2560. 2 to the 4 is 16. 16 times 15 is 240. And then you get 0. And I'm not going to add this. And you add these and you'll get the whatever the corresponding thing is in base 10. Okay, so that's how you represent numbers in different bases. And actually what we've been doing here is we've been converting digits from different bases to base 10, because we understand base 10. Like when I say the number 10 or when I say the number 12, I mean it's 10 plus 2. But all of these I'm saying in base 10. So every time we're doing any calculation, we are actually converting it to base 10. Computers don't do this. Computers actually convert it to binary or hexadecimal. So every time you say 10 to a computer, it actually converts it to A, or it might convert it to 1010, depending on what program is being run. Okay, so all of us have a base that we like, and we use that, so we convert everything to that base. But there's nothing special about 10. It's just a preference that we have based on our experience. Now we're going to go in the other direction. Suppose I give you something in base 10, how do I convert that into binary expansion? And this we'll do by a very nice algorithm. It's a recursive algorithm, if you know what that means. If you don't, that's totally fine. So the way it works is I'll just do an example. It's easiest to do by an example. So the question is, suppose I give you a number, let's say 25 in base 10, and I want to convert it to base 2. Okay, and I'll just tell you the algorithm, and you can think about why that works. So the first thing we'll do is we'll find the remainder and the quotient when 25 is divided by 2. So let's start with 25, and then I'll find mod 2, or I'll write it in more detail. I'll find 25 mod 2, and here I'll find 25 div 2. So 25 mod 2 is 1 because 25 is odd. And 25 div 2 is what is the quotient when you divide 25 by 2. So it's 24 divided by 2, which is 12. And you repeat. So you find 12 mod 2, and then you find 12 div 2. So 12 mod 2 is 0 because 2 divides 12, and then 12 div 2 is 6. You repeat. You do 6 mod 2, then you do 6 div 2, and 6 mod 2 is again 0 because 2 divides 6, and then 6 div 2 is 3. We're almost there. Three mod 2 is 1, and 3 div 2 is also 1. So you stop when your div part becomes less than the base. So here you in this case, our base is 2 and 1 is less than 2, so we stop. Okay, so now we did all this. So what is the decimal expansion? Sorry, what is the binary expansion? The binary expansion is simply you collect all of these together. And so I'll get 1, 1, 0, 0, 1, 2. And so my answer is that 25 base 10 is the same as 1101 to the base 2. So that's how you would do it. Let's do one more example. Let's now convert something to hexadecimal. So let's do a slightly bigger number. Let's do 625. No, I'll have to divide that. Let me just stick. So let's do the same example. Now let me try to convert 25 to hexadecimal base. So 25 in base 10, I want to convert to base 16, which is hexadecimal. So I'll start with 25, and then I'll find 25 base 25 mod 16 and 25 div 16. So 25 mod 16 is what is the remainder you get when you divide 25 by 16, and that turns out is 9. And what is the quotient when you divide 25 by 16? That is 1. Oh, and 1 is less than 16, so I just stop here. I don't have to go any further. And then I just collect all the leaves of the tree, and that's my answer. It's a very simple process. You just have to recursively do it systematically. Of course, I did these things. Of course, it's easiest to do for binary expansions. For like hexadecimal expansion, you have to divide by 16 and then find the remainder correctly. And it's not something you will do by hand. Typically, you just write a program to figure this out for you.